Hello, welcome back to another video. I trust and hope that you are all doing well and staying safe. So, we want to continue looking at another concept in mathematics. And the concept that we're going to be looking at is the concept of Lagrange multipliers. We're going to look at the concept of Lagrange multipliers. Right? And we want to just explore a few things within this video. We're going to look at what really are Lagrange multipliers and how can we apply this concept of Lagrange multipliers to real life. Um, there would be many teaching strategies that teachers use out there. Many teachers would have taught students how to solve equations, system of equations using the concept of Lagrange multipliers. But what this video is geared towards today is really to show you how you can apply what you would have been being taught thus far. All right, so we can just remind ourselves, what are Lagrange multipliers? Now, Lagrange multiplier looks at introducing a variable with the aim of optimizing a given task, given that you're subjected to some constraint. So when we talk about Lagrange multipliers, it looks at introducing a variable so that you're able to optimize something based on some situation, right? Given that there is some constraint. And we're going to look at that a little bit more. And when we talk about optimizing, we talk about maximizing or minimizing, right? And one applications that Lagrange multipliers can look at, they talk about production. If you're going to be talking about production, you want to talk about minimizing your cost, right? If you're going to be talking about so if you're going to be talking about production, you want to maximize production, right? But if you're going to be talking about costs, then you want to minimize your costs. So we're going to look at a question, just an application question of how you can apply Lagrange multiplier. So let us say that you want to produce a box. You want to produce a box. So here you want to produce a box, and we're going to be even a little more specific. We're going to say a rectangular box. So you want to produce a rectangular box. Right? And this box is going to be an open top box. So we want the box to be an open top rectangular box. With the base of the box, with the base of the box costing with the base of the box. But before we touch into that, let's just fix this up a little bit. So we want to create an open top rectangular box. We want to create an open top rectangular box with a square base. All right, so the base of the box is going to be a square. Now the volume of the box must be 375 cubic centimeters. The volume of the box must be 375 cubic centimeters. The material and we're just going to fix up our A here. The material. So the material for the base of the box is going to cost $6 per centimeter squared, or per squared centimeter. Let's correct ourselves and use the correct terminology. And for the side, it will cost, let us say, for the side, it will cost $4 per squared centimeter. Now, we want to find the dimensions of the box. We want to find the dimensions of the box. We want to find the dimensions of the box that will minimize, minimize the cost of the material, materials used. So here we're going to look at how can we find some dimensions, and we're talking about the dimensions of the length, the width, the height, so that we end up getting our box to be 375 cubic centimeter. But we were able to minimize the amount we have to pay to produce or to build this box. Now, let us look at what we have to work with. So we're building some box, and I always like to visualize what I'm building. So in this case, I'm building a box. So I'm going to go ahead and I'm going to draw my box. Here is what a visual of my box will look like. And since it's a square base box, we know both the length and the width will have the same dimension. We're going to call that X. And the height is going to be Y. Now, there are two things that we need to look at. One, we know that the volume of the box, the volume of the box as it relates to, we're going to call that Vxy, right? Taking into consideration all three dimensions, is going to be, we know the volume of the box of our cuboid, which is what our box here is representing, is going to be x times length times width times height. So that's x times x, which is going to give us x squared times our height, which is y. And that must be equal to 375. Now we want to find a cost function, right? And we have to find a cost function as it relates to the dimension of the box, right? So we know that the materials per squared centimeter for the base of the box is $6, right? So the area of the box is going to be x squared. So that's going to be 6 times x squared plus the cost for all four sides, right? Now, since it will cost me $4, it will cost me $4 per squared centimeters. There are four sides, 1, 2, 3, and 4. Right, and the area, we know this is x, so this is going to be x. The area of one side is going to be xy, so that's going to be 6x squared plus 16xy. This is going to be my cost. This is going to be the cost for producing the box. And this is what we want to minimize. We want to find some dimension so that it costs us less. We are able to find the lowest possible cost of creating this box. Now, notice that while you want to find dimensions to minimize their costs, the volume of the box must be 375 cubic centimeter. And hence this year we're finding dimension subjected to some constraint. We're finding dimension that will minimize the production of the box, but the volume must be 375 centimeter. So though we want to find some dimensions that will minimize this cost for producing this box, we still are working with some constraint. And the constraint in this case is that the volume of the box must be 375 cubic centimeters. And when we want to maximize or minimize something subjected to some constraint, then in order for us to do so, we must use Lagrange multiplier. Right? We must use Lagrange multiplier. Now, to minimize a function subjected to a constraint, the minimum of a function when subjected to a constraint can only occur when the gradient vector of the function is parallel to that of the constraint. So in essence, what in order for us to minimize the cost, find the minimum, the dimension that will minimize the cost of the box, we want to find the gradient of the cost that is parallel to that of the gradient of the volume of the box. Right? And for this, we know that if the cost is parallel to that of the volume, then the cost, the gradient of the cost is going to be equal to some constant, and we're going to call that constant lambda times the gradient vector of our volume. Now let us find the gradient function for the cost function that we have. And we know that we're going to find the gradient of the cost with respect to x, the partial derivative with respect to x, and that is going to be 12x plus 16y. And we're going to do the same thing. We're going to find the partial derivative or the gradient function with respect to y, and that is going to be 16x. And you'd have been introduced to this before. We can always go back. So we're differentiating this function with respect to x. That's going to give me 2x. We bring the 2 in front, we multiply it by 6, and we subtract 1. That is going to give me 2x. And we are differentiating 16xy partially with respect to x. So the y becomes a constant. We leave it as is. We don't trouble it. And the x here, we know when we differentiate a variable, we're going to get a constant 1. So that's going to give me 16y. Right? Now, we're going to differentiate this as it partially as it respect to y. Because there's no y variable attached here, and we're differentiating it partially with respect to y, we treat it as a constant. So it becomes sorry, we treat it as a constant, and so it will just disappear, right? And so we're going to differentiate this with respect to y. When we differentiate y, it becomes 1. So we're left with 16x. We're going to do the same thing for our volume function. We're going to do the same thing for our volume function. We're going to differentiate it first with respect to x. That's going to be 2x squared y. That's going to be 2xy, sorry. We differentiate x squared, we get 2x. And so that's the gradient function with respect to x. And now we need to find the gradient function with respect to y. Right? And that's going to be x squared. Y, when we differentiate y, it becomes 1. So we're left with x squared. Now, remember we say that for the production to operate at minimum, the gradient of the cost function must be parallel to that of the volume. The gradient of the cost must be parallel to that of the volume. right? The gradient of the cost must be parallel to some volume. And once this happens, then the gradient of the cost function will be equal to some constant lambda times the gradient of the volume function. So let us quickly look at that with respect to x. The gradient of the cost function, 12x plus 16y, is going to be equal to some constant lambda times the gradient of the volume function with respect to x, that's 2xy. So that's going to be 2 lambda x y. We're going to do the same thing with respect to x. The gradient of the cost function, 16x, will be equal to lambda, that's my constant, times x squared times x squared. Right? And what you notice happening here is that we have what is called a system of equations. We have a system of equations. Notice that here we have a system of equations with 3 unknowns. What are my unknowns? There is x, there is y, and there is lambda. But we only have 2 equations. So in order for me to solve a system of equations with 3 unknowns, I must have 3 equations. So, but there's another equation that we have not taken any into account yet, and that is my constraint equation, which is my volume, which state that x squared y must be equal to 375. So here now we have 3 equations with 3 unknowns, and we have a system of equations, and we're going to be solving this system of equations. And once we're able to solve this system of equation, then we will definitely be able to find the dimension that will minimize the cost of producing our box. So let us solve this system of equations. And what we're going to do, we're going to just choose one of the equation and solve for one variable. I'm going to choose my second equation, and I'm going to solve for lambda with respect to x, right? So lambda, I'm going to divide by x squared is equal to 16x divided by x squared. Hence lambda is equal to 16 divided by x. Right? So I'm going to take the value of lambda and I'm going to substitute it in my first equations. Let me quickly do that. I'm going to take the value of lambda and I'm going to substitute it in my first equation. So that's going to be 12x plus 16y is equal to 2 times 16 divided by x times xy times xy. My x will cancel there, so I'm left with 12x plus 16 is equal to, that's going to give me 32y. Let me add my y here, plus 16y. Right, I can divide through by 6. I can subtract, 16y on both sides. And that's going to leave me with 12x is equal to 16y, which means that y is going to be equal to let me go here. Y is going to be equal to 12x over 16, which means that y is going to be equal to 4 into that goes 3, 4 into that goes 4, so that's going to be 3/4 x. Now that we know the value of y, we're going to substitute that into one of our equations here, and I'm going to choose my constraint equation because so far it's the only one we haven't used as yet. So I'm going to work with my constraint equation, which state that x squared y is equal to 375. X squared, I know that y is 3x over 4, and that must give me 375. So now I'm solving for x. I am going to be solving for x. This should be x cubed, sorry. So x cubed is going to be equal to, x cubed is going to be equal to, and let me correct this. I'm not sure where I'm getting x cubed from. That's a very silly mistake there. So it's x squared y. So x cubed, x times x, is going to give me x cubed. And that is going to be equal to 375. Times, we're going to take that and reciprocate it. So that's going to give me 4 over 3. So x cubed is going to give me 375 times 4/3. That's 375 times 4/3, which is going to give me 500, which means x is equal to the cube root of 500. X is equal to the cube root of 500. And this is a very interesting question here. So now we are going to actually we will indeed have a value for x. X is going to be equal to the cube root of 500. That's 7.9. So x is 7.9 centimeters. And we know that y is equal to 3/4 of x. Y is equal to 3/4 of x. So y is going to be equal to whatever 7.9 is. I'm going to find 3/4 of that. Finding 3/4 of that, which is going to give me 5.9 centimeters. And here we have the value for our dimensions, the length and the width being the same here because we have a square base and the height being 5.9 centimeters. And these are the dimensions that we're working with. That will indeed gives us the minimum cost for producing the minimum cost the minimum cost for producing our box. Alright, so the next video we'll look a little bit more as to how we can apply Lagrange multipliers.